All right, so moving into section number 5, which exploring the TCP/IP link layer. Again, we're talking about basically the data link layer in this case. We're going to take a look at, actually in this case, we're talking about both the physical layer and the data link layer, because we're going to be taking a look at some cabling concepts here. What type of media do we use in an Ethernet LAN? We're also going to look in detail, into detail. We talked about it in the previous section, but we're going to get into detail on what the frame structure looks like. So we're going to do some Wireshark captures and kind of break down the frame structure. We'll talk about different communication types across the LAN. So things like what is a broadcast, what is a unicast frame, what is a multicast frame. We'll talk about MAC addresses as well. So I'm going to do a little exercise with you guys, kind of as a precursor to some of the computing math that we're going to see a little bit later on, where we're going to talk about how to do hexadecimal to binary to decimal conversions. And then we're going to get into a deep dive on our switching techniques, which we kind of talked about already in the previous section. What is a frame switching method? How does a switch operate? And then we'll wrap up this section by talking about duplex considerations with a switch and so on. So that's what we're going to be focusing on. Let's start with the physical layer in this case. Right? The cabling path, how do we interconnect our devices, what are some of the limitations? So distinguishing different Ethernet media options, including the different types of connectors and cables. Yes, for CCNA, you do need to be aware of some of the physical layer concepts that you potentially could be tested on, like what is an RJ45 connector, what is EIA TIA 568A versus 568B, what is a straight through cable, what's a crossover cable, what is a rollover cable. So we'll talk about all that. And then finally, like I said, identifying the Ethernet frame structure, what is a MAC address, and then mastering. Yes, we're going to master Ethernet switch operations. It's not that difficult actually, so it wouldn't be too hard to do that. All right. So again, when we talk about the standards for twisted pair Ethernet, and we talked about this briefly on day number 1, which was, believe it or not, yesterday. We talked about where we came from, right? The concept of using coax primarily was the primary method that we used to communicate. Our backbone was coax, our 10-base-2 network was coax, our 10-base-5 network was coax, but now we've moved over to this twisted pair Ethernet. And so you'll see terms like 1000 base T or gig or whatever. The 1000 obviously represents the speed. Like I said, base represents baseband transmission. We don't need to get into the actual signaling technique, but when we talk about the physical layer, it's really important to understand how we identify modulation. Let me pull up something and I'll show you what I mean by that. And I briefly talked about this in yesterday's discussion, but if I go out to Google and I search on Ethernet category ratings, right? So I pulled up this one here because it's easier to read, but you notice that we see these different UTP category ratings. First of all, what is UTP? UTP stands for unshielded twisted pair. And we'll see some pictures of this a little bit later on, but basically your twisted pair cables are 4 pairs of wires twisted together in pairs. So there's 8 conductors twisted together in pairs, and that's why it's called twisted pair. UTP, or the U, stands for unshielded, which means that you basically have your PVC jacket on the outside and you have your coating on the individual conductors, but there's really no shielding in that particular cable. The flip side of that is what we call shielded twisted pair, which is a cable that has various types of shielding. Cat 6, we have 2 different shielding options, Cat 5 and below or Cat 5e and below. Really, we only have an outer shield to protect the pairs, but we'll talk about that a little bit later on as well. But you'll notice, and this is probably the most important piece to this, as I move up in the category ratings, obviously the speed is going to increase, but oh, it's missing here, of course. The one thing that I wanted to show you is the frequency. The data rate is actually related to the frequency of the cable itself. So again, Cat 1, Cat 2, Cat 3, but you'll notice here maximum frequency. And as I go up into the category ratings, we see that we started at less than 1 megahertz, and then we're now up to 600 megahertz with Cat 7. Think about what that means from the perspective of bandwidth, right? Because how do we recognize ones and zeros? We're not literally transmitting voltages, because voltages don't really, we wouldn't be able to change or modify the voltage fast enough to send 10 gigs or 20 gigs or 40 gigs of throughput. We have to have a way of modulating the signal so that we can understand the ones and zeros, or we can actually represent the ones and zeros as quickly as possible. So what we're doing is we're exciting the electrons on the wire, and then that is generating something called an electromagnetic field, and it's the electromagnetic field that we're actually measuring to identify the ones and zeros. So if we can manipulate that electromagnetic field faster, that then translates to faster bandwidth, right? More bits per second. So that's really the primary difference between, say, a Category 1 cable and a Category 7 or a Category whatever, all right? But there's obviously other differences, right? Because what's the most important concern if I'm trying to push more data through a cable by changing that field more quickly? The fidelity of the signal. We have to be able to recognize that the ones and zeros are the ones and zeros, right? Like I said, I could send you data with smoke signals, right? But it takes a long time to generate those smoke signals, so we're talking about kind of a low bandwidth type of application. What changed when I went from, say, Category 1 to Category 2 to Category 3 all the way up to Category 7? The construction of the cable itself, right? The number of twists per inch or twists per foot, the actual twist patterns in the pairs themselves, and in the case of going from Cat 5e to Cat 6, we actually started to change the physical construction of the cable. So we added that really annoying plastic separator in between all the pairs, and then the cable became a thicker gauge cable and so on. So you're not tested on this kind of stuff on the exam, but there is a physical difference between these cables, and they do operate at different frequencies. So you can't just take a Cat 4 cable, plug it into a 10 gig interface, and hope that you're going to get 10 gigs of throughput. It's the same physical port type, it's the same physical connector, but it's not going to operate the same way. All right, so that's really important to understand. And you know, the baseband transmission, like I said, that's kind of how we got off on this little tangent, is the way that we're generating that electromagnetic field. It's the modulation technique that we use to generate the field. The T just simply means twisted pair. If you see an X, like a TX, the X typically means full duplex, right? A full duplex cable. All right? Now, they talk about here something called electromagnetic interference. All right? Because we're generating an electromagnetic field and we're measuring that electromagnetic field to identify the ones and zeros, obviously the cable is going to be susceptible to outside electromagnetic fields or electromagnetic interference that's generated by transformers and lights and everything else around us. There's always kind of these fields of electromagnetic spectrum in the spectrum that are in the airspace, right? So that's where you get to decide if you're going to use a shielded cable versus an unshielded cable, because you want to make sure that the data is not going to be influenced by these outside electromagnetic fields. All right. The other thing to consider with cabling is it plenum rated versus non-plenum rated? Anybody heard of that term before? Plenum versus non-plenum? What is a plenum rated cable?
For HVAC systems, right?
Well, it doesn't have to be for HVAC, but it's for commercial construction, right? It's for fire codes. a plenum rated cable doesn't release toxic fumes if it burns or whatever. So if you're putting cabling into a multi-tenant building or a high-rise or some sort of commercial property, usually you'll have to get some sort of plenum rated cable to do that. Something interesting has occurred over the past few years that I find pretty interesting as well. And surprisingly enough, a lot of people are not really aware of this. And I only recently became aware of it in the last 5 years or so, but is this concept of CCA cable. CCA is, I don't know why the internet is running so slow today. Let's see. Let's try that again. There we go. So let's say I want to buy 1,000 feet of Cat6 cable, right? And usually that's probably going to be what, about 120, 150 bucks or so, riser cable. So CMR means that it is rated for commercial space, right? So that's a plenum rated cable. But you'll see quite a discrepancy between the prices, right? There's $140, $200, $129. Ooh, 60 bucks. I'm going to get that, right? That's the cheapest cable you can get. But if you look at the description, it tells you this is CCA conductor cable. They're actually making the cable now out of aluminum, and then they're bonding copper to the outside of the aluminum. So it's not solid copper, it's actually aluminum cabling with copper cladding. There is some, it doesn't function nearly as well as solid copper cabling. So if you're ever doing a cabling project or you're trying to buy cabling for a project, make sure that you're using solid copper cabling. I don't know that you would really necessarily notice the difference, as an individual user, but there's definitely a difference, right? Aluminum is not nearly as good of a conductor as copper is.
If you're buying 3850s, you can afford copper cable.
Yeah, exactly. If you're buying an $8,000 or $9,000 switch, 24-port switch, you should probably get solid copper cabling, right? So the Ethernet media standards, yes, there's an organization called EIA-TIA, and this organization really defines kind of all of the standards of cabling, not just for twisted pair Ethernet, but for other other types of cabling standards as well. Telecommunications Industry Association, and I forgot what EIA stands for, Electronics Industry Association, I think, but we'll talk about some of the standards that they define. So when they mention that here, a TIA standard, Category 5 is just one example of a 100 base TX. Again, the X stands for full duplex. We don't really use that too much these days because pretty much everything is full duplex, but remember, we went from token ring to Ethernet, 10 meg Ethernet, which was half duplex, so they had to designate that the cable was full duplex capable. And that had to do with the number of pairs and also the transmit and receive paths. And the maximum distance is 328 feet, like I said, 100 meters. And we're using an ISO 8877 connector, which is an RJ45 connector. That's an 8P8C connector. For 1,000 or 100 base FX, F is fiber, X again is full duplex. And for fiber, you have a whole bunch of different types of specifications. You have short haul fiber, you have long haul fiber, you have different types of fiber, single mode, multi-mode. The specifications there's essentially basically 3 different types of fiber specifications. Let me pull that up because I'm not sure that's in the book as well. There's a single mode, there's multi-mode, and there is laser optimized multi-mode. So let's see if I can pull that up here. So a single mode fiber is a 9 micron fiber. It's called single mode because it uses a single frequency, single frequency to pass the information. So it's a much smaller core. The core itself is made of silicon dioxide, and which is basically glass, and it has a doping material in it called germanium dioxide that changes the index of refraction of that core. And then you have the same cladding, which is also made of silicon dioxide on the outside. Let me do fiber optic cable. So you can see a picture of this, but let me see if we have, yeah, right here. Okay. So the core itself is the silicon dioxide with the germanium dioxide doping material. The cladding is just glass. So we're changing the index of refraction to create a channel to reflect, not refract, to reflect the signal down the channel, right? Light does escape the core, and that's measured in loss, dB loss, but ultimately we don't get a perfect mirror, so what we send in is not always what we send out. And then you might have some PVC coating or plastic coating, aramid yarn or aramid string, which is basically just Kevlar string that's used for tensile strength when you're pulling the cable through a conduit or something, and then your outer PVC jacket. The outer PVC jacket actually does represent something. It doesn't necessarily have to, but generally there's 3 different colors that you're going to see for fiber. All right, so we'll get it. These ohm ratings are optical measurement ratings. We don't need to get into those specific details, but the higher the ohm rating, the more precise the construction of the cable is. So you're going to have less loss, and the cable can support longer distances and more bandwidth and throughput and so on. And typically ohm 3 and above is what you would usually install within, in between buildings and so on. But the orange indicates a multi-mode cable. The distance limitation here is, hundreds of meters to maybe 1,000 meters or whatever, but not 80 kilometers like a single mode fiber. That's usually going to have a 62.5 micron core and 125 micron cladding. You'll see that most of these all have the same outside diameter for the cladding because they want to have similar construction techniques. And then the connector actually represents typically some sort of type of cable as well, the actual physical connector. We don't need to get into that, but this is a 50 micron multimode cable as well. Not as common, typically 62.5 microns. When you get into the high speed, the 10 gig speeds and 40 gig speeds and so on, you'll get a laser optimized multimode, and that jacket is going to typically be an aqua color. So it's a much better construction. It's still a multimode cable. Typically it is 50 microns. And then it's 850 nanometer signal because it's laser optimized. And then single mode typically has, it's an optical specification or standard. It usually has a yellow jacket, and it's typically a 9 micron. They don't have the size here, but it's a 9 micron core, all right? So when you look at these fiber cables, you can see fiber optic cables. You can see the different colors of the jacket and so on, and that will indicate what type of cable it is. Does that mean you can't call some manufacturer and say, I need purple cables, or I need red cables, or black cables? Sure you can. Those particular colors, aqua and yellow and orange, do represent a specific type of cable, but you can see fiber optic cables in any type of color, and you can order them in any type of color, all right? So what they're showing us here are kind of some different standards, not all of them, but some of them. So this is a 62.5 micron multi-mode fiber. You can notice the distance limitation is about 400 meters. The type of connector, again, with fiber, you can have all types of different types of connectors. I'll show you some of the basic ones. So these are some of the types of connectors, and these are not even all of them. There's tons of different types of connectors that you can have with fiber. The connector type itself has no relevance as to what type of fiber it is, because these connectors are available with multimode, with single mode. The connector color does represent something. So you'll see a blue one, a green one, a gray or silver one. Those tend to represent the type of cable, or at least the type of connector. But some of the common types of connectors that you see, there's really only basically 3 of them. You've got the SC, which is called the subscriber connector. This happens to be a duplex SC, so it's got the transmit and receive. But that is what I call the stick and click connector, because you just basically stick it into the port and it clicks in. But it actually stands for subscriber connector. The ST is the straight tip connector. I call it the stick and twist connector, because you stick it on the post and you twist it to lock it in. And then the other common one is the LC connector. This is probably the most common with most equipment today. That's called a lucent connector. I call it the little click connector, because it's about half the size of a regular SC coupler. But they've got others, FPPC, APC, E2000, and so on. But the most common for networking equipment is going to be your ST, your SC, and your LC connectors. But again, it doesn't really matter. I mean, you can get SC patch panels, you can get ST patch panels, you can get SFPs with ST connectors on them, or LC connectors on them, or SC connectors on them. So it just depends on the type of equipment, really. There's no functional difference from a transmission and reception perspective from an SC connector to an ST connector, and so on. So they mention, and the reason I bring that up is because they mentioned the ST, the stick and twist, or the straight tip connector, but you don't have to run an ST connector with this type of fiber. 100 base T, twisted pair Ethernet, or 1000 base T, excuse me, category 5E, up to 100 meters, also an RJ45 connector. SX versus LX. That's important to understand. S stands for short haul, L stands for long haul. So if you see an SX, and the X is full duplex, if you see an S or an L with a fiber indication, that usually will describe whether or not it is a single mode fiber or whether or not it's a multimode fiber. So SX is short haul, that's typically going to be multimode. And again, depending on the size, anywhere from a couple hundred meters up to 550 meters, and some sort of optical fiber connector. Don't know what kind, doesn't really matter, it could be any kind really. Long haul, a 9 micron single mode fiber, and up to 10 kilometers. Actually nowadays they're getting even further than that, up to 80 kilometers without a repeater, which is pretty significant, and that's going to have various types of connectors as well. All right, so lots of ways that we can connect our devices in the LAN. Now, what's the primary difference between twisted pair Ethernet and fiber? There's 2 major things, right? One is susceptibility to electromagnetic interference and static electricity. The other is distance limitations. Fiber allows us to go further distances. Fiber connectors tend to be a little bit more expensive. The fiber cable tends to be a little bit more expensive and more difficult to terminate and manage. But a gig fiber is the same as a gig of copper, right? At least from a theoretical standpoint, they're the same. From a practical standpoint, you're probably going to get a cleaner signal, less loss in a fiber cable, but there's also more stringent restrictions on how that cable gets installed, how it gets terminated, and so on. All right? So with the copper, we have our twisted pair Ethernet. It looks like this. All right, we've got those colors. Ignore those colors. Those colors are not indicative of what you would see. You would have a green pair, an orange pair, a brown pair, and a blue pair. But they are pairs of wires twisted together, and then you have your 8P8C connector. As far as speed and throughput, 10 meg all the way up to 40 gig now, especially with the higher category ratings. Very inexpensive, very small media connector, and a maximum distance limitation of, like I said, 100 meters. Actually, it could be less than 100 meters, depending on the type of speed, right? For example, Cat 6, at 10 gigs, you can only go up to 50 meters or so. So it just depends on, or 55 meters, it just depends on the rating of the cable and so on. But unshielded twisted pair is susceptible to electromagnetic interference and radio frequency interference and so on. We did talk about the different types of speeds as well. We see that here, Cat 5 up to 100 megs, Cat 5e up to 1,000 megs. But there is a new technology, well, it's not super new, but it is relatively new, called multi-gig. And what multi-gig allows us to do is it allows us to take a port which would normally operate at maybe a gig speed, and it allows us to push more than a gig of speed through that particular port. I don't know what they're up to. Yeah, up to 6.8 gigs now. Well, that's the AC. This is the actual problem, right? The problem is with 802.11 wireless and wireless access points and whatnot, we have speeds up to 6.8 gigs, but we only have gigabit Ethernet ports on in our Cat 5 environment. So how do I take an AC access point, plug it into a Cat 5e port, and get the maximum throughput without basically forklifting my environment, upgrading my cabling and switches to support that, that feature? So Cisco created this N-base-T alliance where they are now able to push up to 10 gigs over Cat 5e and Cat 6 without having to change the actual physical infrastructure. It's a very interesting concept. I would definitely recommend that you go take a look at this multi-gig technology, but it gives you the ability to push more than 1,000 megabits through a second through a Cat 5e cable. Cat 6, 24 gauge as opposed to 22 gauge. Cat 5e was 22 gauge, Cat 6 is 24 gauge cable. And again, we have that plastic separator in between and some other techniques to make it a little bit faster. Cat 6 is actually rated up to 10 gigs, but not at 100 meters, at about 55 meters. Cat 6a is rated up to 10 gigs up to 100 meters. And then we have Cat 7, Cat 8, and there's actually stuff beyond Category 8 and so on. But Cat 8 is up to 40 gigs. These are your connectors, your 8P8C connector. Looking at it from this angle, this is pin 1 on the right. This is pin 8 on the left. We'll talk about the color coding schemes after lunch, but with the tab facing down and the cable pointing away from you, like you're plugging it into the wall, the pin 1 is always going to be on the left side. This is your keystone jack, same concept. You guys know what that is. The options that we have with regard to our switching technology is we have the ability to provide something called Power over Ethernet. And there used to be a couple of different versions of PoE. There was a pre-standard version that Cisco created, which provided about 14 watts of power per port for devices like IP phones and cameras and access points and so on. And then 802.3ae came out, which provides basically up to 30 watts of power per port, depending on the type of power supply that you have on your device and what types of devices are connected to provide that power over Ethernet option. Now, I'm not going to get into the specifics of different power classifications for different devices and so on, but we understand that this is just another function, auxiliary function of what a switch does, which is to basically allow for connectivity, but also to power some devices. And we're starting to see more and more devices in our network that are powered by Power over Ethernet functions. Certainly security cameras, IP phones, access points, like I said, and some other devices as well. So one of the things that you will have to know for the exam is what is a straight-through cable versus a crossover cable. But before we get into that, we have to talk a little bit about the color coding scheme that you see here and talk about why we've defined two separate color coding schemes, what the standard scheme that we typically see is versus what you would see maybe in a crossover cable. So the diagram here on the top left represents kind of your standard twisted pair Ethernet termination, what we call a 568B standard. Let me highlight it real quick here. This is your 568B standard. You've got the orange pair, you've got the green pair that's split by the blue pair, and then you have the brown pair at the end. White, orange, orange, white, green, blue, white, blue, green, and white, brown, brown. Now, actually, you know, technically speaking, you don't really need to follow the color coding scheme as long as pin 1 goes to pin 1 and pin 2 goes to pin 2 and so on. But actually, the pairs themselves have unique twist patterns. The orange pair is twisted differently than the green pair, and that's twisted differently than the blue and the brown pair. So it is actually kind of important to follow the color coding scheme because of the way the transmit and receive paths are identified, and also the way that the pairs are twisted individually together. On the right side, you see that we've followed, at least on the right side of this particular diagram, we've followed the 568B standard as well. Again, the 568A standard starts with the green pair. The 568B standard starts with the orange pair. And I would say 99% of your terminations are going to be 568B. Why would I need to swap, say have one end that's a 568A end and the other end that's 568B? What is the reason for that? Well, when you look at an actual termination, and you can see in this particular case, they've actually highlighted some specific interfaces, pins 1, 2, and 3, and 6 in this particular case. This is actually a little bit misleading because this is a crossover cable for 100 meg Ethernet, not gigabit Ethernet. Why do I kind of specifically identify that as something to be concerned with? Because in 100 meg Ethernet, we only used 4 wires to communicate. You only used pins 1, 2, and 3, and 6. You had pins 1 and 2 for transmit, pins 3 and 6 for receive, and vice versa. But when you move to gigabit, all 8 wires are going to be used for transmit and receive. So you need to make sure that not only are you crossing over the green and the orange pairs, but you're also crossing over the brown and the blue pairs. That's what a true gigabit Ethernet crossover cable would look like. All right, but again, why would I need to cross over cables? Let me pull up my paint here again and kind of give you an idea of why we would need this. So if you have, say, for example, a switch, right, and that is connected to a PC. Now this PC is hardwired specifically for transmit and receive. There's a transmit path and there's a receive path. And it just so happens that PC's pairs that are wired for transmit and receive happen to coincide with the receive and the transmit pairs on the switch. So when you plug the cable in, a straight through cable, the receive goes to the transmit and the transmit goes to the receive, and you can actually have, you know, your full duplex communication. But when you plug 2 switches into each other, and you have a, you know, SW1 and SW2, and you plug them in, what ends up happening is that the transmit paths and the receive paths end up matching on the same pins, and that's not obviously going to work. You can't have two transmit on both sides and receive on both sides. You have to have them swapped over or crossed over, and that's what the crossover cable does. It takes the transmit path on one side, it crosses it over to the receive path, it takes the receive path and it crosses it over to the transmit path. So in essence, what we're saying here is that if the devices are the same, we would want to use a crossover cable. If the devices are different, we typically would not use a crossover cable. So for example, a PC to a PC, we would use a crossover cable. A PC to a router, I wonder. What is a router designed to be plugged into? A switch. Yeah, could be another router, yeah, especially if it's like a serial connection or an Ethernet, a point-to-point Ethernet connection. But a router is really technically designed to be plugged into a switch. Remember, this whole concept of crossover and straight through, this is all physical layer stuff. It doesn't really matter if it's layer 3 versus layer 2. It matters as to how the device is physically hardwired. And a router is hardwired to be able to plug into a switch. PC is hardwired to be able to plug into a switch. So guess what? If I plug a router into a PC, what does that mean? That means that we're going to run into the same problem where the transmit path is mapped to the transmit path and the receive path is mapped to the receive path. Now, in modern networking technology, do we really concern ourselves with this too much? Not usually, right? Because we have that auto MDIX feature where the devices can auto sense what they're plugged into, and they can reprogram themselves automatically or internally to be able to communicate based on the transmit and receive paths. All right? But there is a diagram in the book that kind of describes when I would need a crossover versus a straight through. Certainly when all the devices are the same, switch to switch, router to router, I would need a crossover. But again, typically a router to a PC, because a router is designed to plug into a switch. A PC is designed from the physical layer perspective to plug into a switch. So that would require a crossover. One that's missing here is maybe a hub to a switch. Again, a hub and a switch are at the physical layer basically the same thing, so that would need a crossover cable as well. All right? When we talk about optical fiber, we did talk about everything in this particular diagram here. You have your core, like I said, your cladding, your outer PVC jacket or your coating, and maybe even some other protection material outside of that. But again, the diameter of the core is representative of the type of fiber optic cable. This particular core is 9 microns, which means this is a single mode fiber as opposed to multimode, or even laser optimized multimode. All right? We talked a bit about the idea of multimode versus single mode. A multimode cable allows multiple frequencies of light through the cable. And that's supposed to be able to identify multiple communication paths or multiple communication processes. So the multimode fiber, by definition, is going to be different than the single mode fiber in that it's going to allow more than one light frequency, right? Hence the term multimode. Again, the multimode core is going to be much thicker. Relatively speaking, of course, 62.5 microns, or at least a minimum of 50 microns, as opposed to the single mode. You'll also notice that we see a reference of N here on the diagram. N in this particular case is the index of refraction. Again, the core is made up of silicon dioxide with a doping material mixed into the silicon dioxide. Usually, like I said, it's going to be like a germanium dioxide type of component. And that's to change the index of refraction. And the idea is that from a physics perspective or a physical properties perspective, that we're trying to contain the light source into the channel, into the core, so that we don't get any refraction, but we simply get reflection. Refraction is bad. That means light escapes the core, goes into the cladding, which is essentially loss of signal. But again, that's going to happen. There's no way to prevent that from happening completely. You're always going to have at least some loss in the cladding. Now, the cladding itself is usually about 125 microns, this diameter here. That's pretty consistent across many manufacturers because they want to make sure that we're not losing, or that we have the same basic construction principles for the protective material, the aramid yarn and outer jacket and the coating and stuff like that. All right. Also, multimode fiber tends to use LEDs as a light source, light emitting diodes, whereas single mode fiber or SMF tends to use lasers as a signal generator for the light source. All right. But, and there's some obvious differences there with regard to how far we can go, what kind of distances we can go, and so on. All right, and they do break that down in the table here. Multimode fiber tends to use LED transmitters. Typically a lower speed, lower bandwidth, shorter distances, usually less expensive, especially for the transceivers. The transmitters and the receiving components are going to be less expensive. Single mode, we use a laser as a light source, high bandwidth, much longer distances, significantly longer distances actually, and a little bit more expensive. We also talked briefly before the break about the different fiber connector types. LC, like I said, is a lucent connector. I call it, like I said, the little click connector. A dual LC, or what we call a duplex LC, and most fiber, by the way, is going to come in some sort of duplex fashion, right? Because the fiber strand itself is a single path. And if you want to run in full duplex mode, you have to have two fibers because you have to have a transmit path and you have to have a receive path. So even though the fibers are constructed separately and they're basically just bonded together or clipped together, they're really independent channels of communication. So the LC connector is our lucent connector. We have the single and the dual. This ST, what we call a straight tip connector. That's our what I call the stick and twist connector. And then we have our single SC subscriber connector and MTRJ. That's a pretty popular one as well. Usually for like network interface cards and stuff like that for computers, you'll see an MTRJ connector. I don't know why they have the cover there, but that's kind of irrelevant. But you can see that there are many different connector types. In fact, I think there's close to 50, 60, or 70 different types of connectors now. It's a pretty broad spectrum of connection types that we have. When you establish fiber connections into your enterprise, again, the benefit of running fiber over copper outside of the distance capabilities that you see, the benefit is that you're going to be less susceptible to outside interference. You're also going to be able to go larger distances, of course. You're going to have the ability to you know, maybe run in different environments that a copper cable might not work in and so on. And generally speaking, you're going to get probably a little bit less loss with fiber than you would with copper, at least from a theoretical standpoint. So typically what you would have is you would have maybe an SFP in your device. And this is what the SFPs look like. It depends on you know, what type of cable you're trying to connect, but it's a small form factor pluggable transceiver. That's what SFP stands for. And we're still slow there, so I'm going to go over here, SFP. All right. And this is what these look like. These are some LC, duplex LC SFPs. And you can see that they have, they're laser rated, obviously. Well, not obviously. I would say you would have some LED ones and you can have some laser optimized ones as well. So I don't know if you can see it here or not, but let me see, view image. Yeah, you can see it there. See how this says class 1 laser? So this is a laser transceiver. It's rated at 1310 nanometers up to 10 kilometers. So this is like a single mode SFP. So they're not all the same, right? And you can see you've got some copper ones here as well. There's an RJ45 SFP and so on. And what you would typically do is, this is the type of equipment that would go into your switch or your device. And then you would have maybe a fiber patch panel that would allow you to connect or interconnect your devices together. So you might have a panel that comes from the service provider or the from one building to the other, and then with these fiber patch panels, you can get just really any kind of connector here. Let me see. Here's an example of one. And this particular case, it looks like those looks like kind of a non-standard connector type there. Let me see if I can find one that has more of a standard connection. Let's see. So anyway, you guys get the idea. You have all of these different connector options. And again, the connector type has no bearing on the actual fiber type. Whether it's single mode or multi-mode, doesn't really matter. It doesn't really have any particular bearing on the type of connector that you're going to have. So you have push-pull connectors, you have what we call bayonet connectors, you have threaded connectors, and so on. And the book does describe really kind of some of the different ones here. LC, which they call a local connector, but actually it's actually the term that was most commonly used as lucent connector, because that was the company that came up with that form factor. It's a very small form factor, pluggable, and that's what we saw with the SFP modules. The subscriber connector, reason it's called subscriber is because typically it was used for the equipment side. And then you would have your straight tip connectors, which would be used for the patch panel side. But again, you can get SC patch panels, you can get LC patch panels, you can get obviously ST patch panels, and so on. All right, the SFPs, like I mentioned before, provide us the ability to have different types of connections to different interfaces or to the same interface on a switch. So maybe I have a requirement for single mode fiber connections to a particular switch. I can get a single mode SFP module and I can connect it to that switch. It makes it a much more flexible environment because we have the ability to basically interchange those parts based on what our connectivity requirements are and so on. All right, and again, SFP modules don't necessarily have to be fiber. They can be copper as well, twisted pair Ethernet, and so on. All right, so let's get out of our physical layer. Now let's get into the data link layer, and specifically, we're going to be talking about an Ethernet frame. Now, there are two types of Ethernet frames that are available. 802.3 Ethernet, which is an IEEE specification, and Ethernet 2. If I open up Wireshark and I start doing a capture in Wireshark, you will see that most of the frames that are being generated by Wireshark are going to be Ethernet 2 frames. All right, let me go ahead and pull this over, and I'll start doing a capture on my wireless interface. Now, when I do this capture, you have to keep in mind that we're not going to be seeing the preamble or the start of frame delimiter, because again, those are components of the frame header that are primarily physical layer functions. They perform a physical layer function. The preamble is 8 bytes long, and it's basically just a sequence of ones and zeros that are used to do synchronization of the signal itself. So it's a pattern of ones and zeros, if you will, that provides us the ability to do that, synchronization. It's a way for us to ensure that the receiving host is ready to receive the information from the sending host. So that's why we don't see the preamble captured in the Wireshark capture. That should be enough. So I can grab any one of these frames here, and you can see that this is an Ethernet 2 frame. All right. Now, it's a very simple format. We've got destination MAC, source MAC, and type field. We saw this before. This is nothing new. We saw it when we were talking about this stuff yesterday. Destination MAC is a 6-byte MAC address. The source MAC is a 6-byte MAC address. But even the MAC address itself has components that contain special meaning, right? You see specifically 2 bits here that represent specific functions of the MAC address. I'm going to talk about what those 2 things are in a second, but before I finish up, I want to talk about the rest of the frame here. So let me pull up the frame again. You've got your preamble. Like I said here, it's an 8-bit field alternating 1s and 0s for synchronization. You've got inside that preamble something called an SOF, which is a start of frame delimitator. That's typically 1 byte, the last byte of that preamble field. But again, that's really just used for synchronization and to indicate to the client that, okay, now we're going to start processing this data as an actual frame. All right, so really technically the real first field of an Ethernet frame is the destination MAC. Then you have the source MAC, and then you have your type field. All right? Now, the payload, anywhere from 46 to 1,500 bytes. I think I said 64 before, I apologize. But anywhere from 46 to 1,500 bytes. So you have a minimum size and you have a maximum size. Anything that sits below 46 bytes in the payload is considered a runt, and generally those frames will be discarded. So oftentimes you'll see applications and protocols add padding bits in that field to make sure that we have at least 46 bytes of payload. What about stuff that's above 1,500 bytes? Is it allowed? Yes, it could be allowed, but you would have to configure the devices to recognize something called jumbo frames. You can go up to actually 9,000 plus bytes inside the payload field. But you do have to program your devices to be able to recognize that size. What about the frame check sequence? We've mentioned that a couple of times, but we never really talked about the specifics. It's a 4-byte field, which means it stores 32 bits of information. And what we do is we do something called a CRC, or a cyclic redundancy check. So I go through and I generate all of my data. I generate my frame, which includes my entire payload as well as the frame header. And I do a mathematical calculation. Basically, it's a mathematical hashing function. And I generate a value that goes into that field. All right, now I send the data on to the destination. Whoever's processing this frame, or whoever receives the full frame, will do the same calculation. They'll process all this data. They'll process all the data all the way up through the payload, and they'll actually perform the same calculation. If they come up with the same number in that CRC field, then they know that the frame has not been modified, it hasn't been adjusted or changed in any way, and so we can verify essentially the integrity of the frame. What happens if the CRC calculation fails? What do we do when the CRC calculation fails? We drop the frame. Well, not at layer 2, right? Layer 2 doesn't have any function for retransmission or guaranteed delivery. Now, it could be a function of TCP or some other layer, but you're right. The frame does get dropped, and then typically, because we're running TCP or the application itself has something built in, we will go ahead and retransmit that particular frame. Now, the reason why they don't talk about 802.3 Ethernet, in fact, let me pull up an 802.3 frame for you guys, and I'll show you the difference, and we'll talk about it. We do see 802.3 Ethernet. Typically, 802.3 Ethernet is going to be reserved for network device communication, like spanning tree frames are going to be carried inside of 802.3. CDP, DTP, VTP, these are all kind of layer 2 switching protocols. They're going to be carried inside of 802.3. So what I want to do is I'll pull up an example, because I can't capture any on our network. We're not running any of those protocols on this network, but let me pull one up, all right? So here is an 802.3 frame, and you can see it actually has what appears to have a lot more kind of components to it than a standard Ethernet 2 frame. We still have the same 12 bytes in the beginning, right? And by the way, it still has a preamble and a start of frame delimiter. We still have the destination MAC, we still have the source MAC, but instead of a 2-byte type field, we have a 2-byte length field, okay? So this length field identifies the size of the layer 2 frame. And then we have what we call the 802.2 snap header. This purple box, the orange box, and this kind of like baby blue box or aqua box. Oh, that one's kind of more aqua, but DSAP, SSAP, and control, this is what we call the LLC function of 802.3 Ethernet. And you've probably seen this before when you talk about Ethernet in general. People always mention the MAC sublayer and the LLC sublayer of Ethernet. That is only specific to 802.3. Ethernet 2 doesn't have a MAC sublayer and an LLC sublayer. But for all intents and purposes, DSAP and SSAP are basically like the type field in Ethernet 2. It allows us to identify the protocol that's encapsulated inside of Ethernet. So it could be spanning tree, it could be CDP, it could be VTP, whatever. The destination service access point and the source service access point allow us to identify the protocol that's actually carried inside the frame. So this byte, and this byte, which are actually take up part of the data field. Remember, it was 46 bytes to 1,500 bytes in Ethernet 2, right? So if you look at the way that this data field is set up, 43 bytes to 1,497 bytes, that tells you that actually the DSAP, the SSAP, and the control fields are kind of a subset of the data field, or at least is taking a portion of that data field that normally would be free if it's an Ethernet 2 frame. So if you do see references to MAC sublayer or LLC sublayer, you're talking specifically about 802.3 Ethernet and not Ethernet 2. And by the way, other IEEE specifications of LAN communication have the same kind of split function, the MAC sublayer and the LLC sublayer. But again, we don't talk about it that much anymore because predominantly most of the frame types that we're going to be capturing are going to be Ethernet 2 frames because that's what typically most clients are going to be using. All right, now what types of communication can I have within the LAN? We have Unicast, which is what? 1-to-1, right? Meaning a single source MAC, a single destination MAC. We have Broadcast, which is 1 to everyone. All right, there's only actually one broadcast address at layer 2, and that's all Fs, or basically 48 bits of 1s, 6 bytes of 1s. FF, 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 okay? But what about multicast? All right, now again, it's a little bit beyond the scope of what they're trying to demonstrate here, but I think it's kind of important to know. So I will give you a real quick crash course in multicast, all right? And the benefit of multicast and why we would have multicast inside of our enterprise. So let's say, for example, I didn't have multicast, but I had a server that was generating some sort of data that needed to be passed to a bunch of different clients. Let's say, for example, it's maybe a video stream or something that I'm trying to send to lots of different clients. And I've got my infrastructure here. I've got this server is connected to this switch, and then that switch goes to that router, and maybe there's another router here, and then I've got maybe a switch here, and a switch here, and a switch here, and then I've got, you know, a client, and 2 more clients over here. All right? And let's say, for example, this particular client wants to receive that stream. Well, guess what's going to happen? I have to generate that stream and send it down to the client. And maybe that's Unicast. All right, let's assume we don't have multicast in this particular case, and I had to duplicate that stream. And then all of a sudden, another client wants to get the same stream, right? And now I have to duplicate that stream down to that client, and vice versa. And you get the idea, right? So as each client needs that particular stream, what's going to end up happening to either the server or the upstream links? They're going to be flooded or overwhelmed with the duplicate amount of traffic that we're trying to generate. Does that make sense? So these are separate individual streams of information, even though it's the same information. Those are separate individual streams of information, which means we're going to overwhelm this link. It's going to run out of bandwidth, or the server's going to run out of resources to be able to send that data. So that's where multicast comes into play. In multicast, what you have is you have a, let me do a new diagram here. You have your network, and you have your multicast source. Again, same server. Your multicast source, again, connected to its infrastructure, and maybe a router, and then I've got a couple of different clients connected to each of these switches here. All right? And so you've got multicast listeners and you've got a multicast source. And so what happens in this particular case is this server has a specific individual address. We'll just call it star. That asterisk represents the address of that particular server. And it has an individual group destination address. We'll call that G because G stands for group. Well, guess what? That destination address is a virtual IP address in the Class D space in IPv4. Do you guys happen to remember? We'll talk about it obviously later on, but do you know what the Class D space range is? 224 to 239, right? In IPv4, that's your Class D space. That's your multicast space. In IPv6, it's anything that starts with FF, all right? So we're sending the traffic to a virtual IP address. It doesn't belong to any one physical device. It actually belongs to nobody. It's a virtual IP. That is what we call the multicast group address. So let's say in this case it's 224.11.11.18. All right? We're sending the traffic to 224.11.11.18. All right? Now, what happens is a client, maybe this client right here, wants to get that stream. Now, how does the client know that it wants that stream? Because you launched an application that says, I'm going to subscribe to that stream. It could be through a web browser. It could be through some sort of application that's designed to look for traffic from that particular group. Or it could be basically a device that's programmed to listen to traffic in a particular multicast group. Things like OSPF routers and EIGRP routers, they participate in the domain by participating in multicast communication. So you have several moving parts here. You've got the server that's generating the multicast stream. You've got the client that wants to join the stream. But we have to be able to build the infrastructure to support the dissemination of that information. So there's basically three things in multicast that allow multicast to work. There's some sort of multicast routing protocol. PIM, for example, would be an example of one of those multicast routing protocols, protocol-independent multicast. You have some sort of multicast management protocol that allows clients to join and leave multicast groups, pretty much only one these days, IGMP, the Internet Group Management Protocol, that allows us to join and leave multicast groups. And then you have kind of a secondary function, snooping. I'll just put snoop. And that's a switch function. Switches by default will treat multicast traffic as broadcast traffic, which means they'll flood it unless they're running some sort of IGMP snooping where they can identify where multicast traffic is going to go. So I don't want to get into the whole concept of dense mode multicast and sparse mode multicast and rendezvous points and, you know, shared tree versus shortest path tree and all that stuff that multicast includes. But let's say that this is a brand new environment and I'm running protocol independent multicast routing on this network. So what's going to happen is we're going to flood and prune that initial multicast traffic. It's going to get flooded through the network to everywhere, and then it's going to get pruned back. Now the reason to do the flooding is to let everybody in the network know that that multicast traffic is available. So the routers basically are building a multicast routing table that says, oh, we've now identified that the .18 group exists and it's available from this particular location. So inside each of these routers now, they are aware that the 224.11.11.18 multicast traffic is available. But it's already been pruned back all the way to the edge. So that multicast stream is being sent out, but it's being blocked at that router. Now what's going to happen is when a client wants to join a group, it's going to send an IGMP join message to the upstream router, to its local gateway. So say, hey, I want that stream. That router says, do I know that that stream exists? It's going to check its multicast routing table and say, oh yeah, I saw that flooded through the network before. I know where the source is, so I'm going to go ahead and send that request up to my upstream router saying, we need this stream now. And then this router, because it's actually participating in that, well, not participating, but it actually is connected to the subnet where the source of that multicast traffic is, it's going to open up the little floodgate, and then that stream is going to be able to pass down to that router. Now that router will send the stream out, and normally the switch would simply flood all that to every port, but because of IGMP snooping, the switch actually knows what ports to send that traffic to. All right? But that stream is still filtered off of that interface. All right? But now let's say this client here says, hey, I want that stream. So it sends an IGMP join message. That router then instructs the upstream router, hey, we need the stream. And it's up to this router then to duplicate that stream and send it down to that downstream router. We're still only sending one data stream from the server. The router is the one that's actually duplicating those packets and sending those packets downstream. Much, much more efficient than the server having to constantly generate additional streams. All right? What is the one characteristic, and we're going to talk about this in the next section as well, but what is the one characteristic of a MAC address that you guys are always told, right? It's called a hardware address for what reason? It doesn't change. Why doesn't it change? I mean, you can change it, but why doesn't it change? It's burned into the card, right? It's part of the chipset. It's a MAC address that, and generally we're always told that MAC addresses are burned into the device, right? They're physically assigned to that device. So when it comes to communicating, when it comes to building a PDU, the MAC address is something that we can always discover because the MAC address is burned into the destination device and it's burned into the source device and it's just part of the communication. But what about multicast? We're not sending this traffic to a specific host, are we? We're sending this traffic to a virtual IP, okay? But there has to be a way to generate a layer 2 address as the destination, because we still have to build the frame. The frame still has to have a destination MAC, right? And that's where we get into the well-known OUI for multicast, which is essentially the first 5 or the first 24 bits of the address is 00005E. Every single IPv4, let me actually do this in Notepad. Every single IPv4 multicast stream or multicast frame is going to have that same OUI, that same 00005E. Now, our multicast address was 224.11.11.18. So what we do is we take the last 23 bits of the packet, of the destination IP, and convert that to hex. That becomes the last 24 bits of the MAC. So 11 is 1, 2, 3, 4, 1, 2, 3, 4. And then the other 11 is 1, 2, 3, 4, 1, 2, 3, 4. And then 18 is 1, 2, 3, 4, 1, 2, 3, 4. All right? We'll get into that a little bit later on. And then to convert this to hex, we just break it up into nibbles. And then we convert each nibble to its corresponding hexadecimal character. So that's a 0. This is an 11, which is a Bravo. 0, Bravo, 1, 2. And that becomes the last part of the MAC address. 0B dash 0B dash 1, 2. 1, 2. All right? Again, you're not going to have to do that for the test, but that's how we derive the destination MAC address for any destination multicast IPv4 address. In IPv6, it's a similar function, just a different OUI, and obviously we don't use the 128 bits. Why it's the last 23 bits, I don't know. I don't know why they just didn't do the last 24 bits. There's got to be a reason. There's always a reason that they do that. But there is a problem with that because since it's the last 23 bits, this bit can be anything. It could be a 1 or it could be a 0, which means that we have potentially two different IP addresses that result in the same destination MAC address. But that's okay. We don't run into that in too many cases as a problem. All right? So I know that was kind of beyond the scope of what they were talking about here. They basically just said multicast is communication where information is sent to a specific group of devices or clients. Unlike a broadcast transmission, in multicast, the clients must be members of the group to receive that information. Well, we become members of the group by joining the group, and we use IGMP to do that. And there's multiple versions of IGMP, and each one of them have specific functions and so on. So what about this MAC address? Right? A MAC address uniquely identifies a client at layer 2. And it is sometimes called a burned-in address or a hardware address because it is hard-coded to the network interface card, and it represents a couple of different things. There's actually basically 4 different parts of a MAC address. There's something called the OUI, which stands for Organizational Unique Identifier, which basically identifies the vendor. But the OUI piece, the first 24 bits, is actually broken down even further because there's a couple of bits in the OUI that represent a specific function. If I go back to my wire short capture, we can see that in the capture here. It's the 7th and the 8th bit. Out of these 24 bits, these are 24 dots here. The 7th dot and the 8th dot represent these special bits. One is called the LG bit, one is called the IG bit. I think in the book they call it the UL and the IG bit. UL is universal or local, IG is individual or group. But it's the same concept that we see in a Wireshark, local or global versus individual or group. So this 7th bit is going to be a 0 if it is the burned in address, meaning that if the MAC address hasn't been modified in software or changed for any reason, that 0 represents the fact that the MAC address is the real MAC address of that device, not an altered MAC address of that device. Does that make sense? This bit, that's why they call it local or global. Global means globally unique. And technically speaking, every MAC address should be globally unique because they're uniquely identified and uniquely assigned by the IANA. At least the first 24 bits are. The last 24 bits are managed by the vendor. All right? This 8th bit represents the IG bit. Is it an individual address or is it a group address? Group meaning, is it multicast or broadcast? In other words, is this a frame that's destined for multiple clients? So both of these bits being 0 would mean that this is a unicast frame using the globally unique burned-in address. You can change your address. I actually have an application called TMAC, or Technidium MAC Address Changer. Let me pull it up real quick. And it provides me the ability to modify my MAC address in software, and I can pick my adapter. It's a free application. I recommend getting it for a reason that I'll explain here in a second. But and you can pick your adapter. You can say, give me a random MAC address, or let me pick, you know, what I want to look like. Basically, do I want to be an Apple device? Do I want to be a Sony mobile device or whatever? Or you can just simply type in whatever number you want. And then you can apply that. And then whenever the device generates frames, it's going to apply that MAC address as the source of those frames as opposed to the burned-in address. I found this to be really useful when I'm traveling through airports, particularly airports where you have to pay for the internet. So you get like 30 minutes for free and then you have to pay. Well, if you change your MAC address, you get another 30 minutes for free. So you just keep changing your MAC address and you don't have to pay. And it works very well, all right? But you may have to spoof a MAC address or change your MAC address for testing purposes or other reasons. So the MAC address itself is 48 bits total, or 6 bytes. Like I said, the first 22 bytes, or 22 bits I should say, represent the vendor. These 2 bits are used for, is it an individual or group address? Is it globally administered or is it locally administered? And then the last 24 bits are vendor assigned. But let me ask you a question. Do these MAC addresses have to be globally unique? No. In fact, what is the scope of a MAC address? In other words, where does a MAC address remain important versus where does a MAC address no longer necessary? I didn't ask that very well, but you get the idea, right? Right. Anything past a router, it doesn't matter. Because layer 2 addressing can only be used by switches or other devices within a common subnet. Once I go beyond a router, my MAC address is irrelevant because I use IP to communicate beyond the router. So yes, MAC addresses are globally unique, but they really only technically have to be unique within the LAN. They don't really have to be unique beyond the LAN. Actually, probably the next hop they need to be unique because you don't want the router learning the same MAC address from 2 different interfaces. But they don't technically have to be globally unique. All right?
Is it possible to change your MAC address to something that has that globally unique address bit to 0?
It is. This particular application, let me give that a try. So this particular application here, let me try and change my one that's not going to affect my wireless here. So I'll just change VMnet 8, right? So if I put in here 001122555555, right? And I do a change now, it works just fine, all right? But that's because this is a virtual adapter. If I tried to do that, let me reset that back to the original. If I tried to do that on my physical interface, let's see, I think it's just this one right here, Ethernet. Dell, yeah, that's my Ethernet, Intel Ethernet connection. If I tried to do the same thing here, 001122555555, it should give me, it should say that I can't do that. Let me try that again. I just erased it. 001122555555. Change now. And yeah, it did change it. Well, what the heck? Let me try my wireless. It should give me a warning and says you can't do that because you're supposed to set that bit, that 7th bit, to a 1. But it doesn't appear to be that this there it goes. Yeah, failed to change the MAC address. The first octet has to be a 02, right? Which means basically they're saying, I can't change your, this is a real interface that is actually communicating on the network. So you're supposed to set that bit. Now, I mean, the reality is as long as the application allows it, like you could probably come up with some hacking application that allows you to actually change it or keep that bit as 0. I'm sure there's applications out there that do that, right? The operating system itself isn't really necessarily blocking that. It's probably the application that's blocking that because they're following the rules, right? Which is if you locally administer your MAC address, you have to turn that 7th bit to a 1. All right? And that's a good question because if that rule didn't apply, it would be very easy for you to spoof anybody's MAC address, anybody's real MAC address. By setting that bit to a 1, that kind of eliminates that as a possibility. All right? As far as how MAC addresses are written, this is probably not a valid format. Let me pull it back up here. You would probably never see kind of a mix of dashes and dots. That's probably a typo. There probably should be a dot there. But you could see, groupings of 16 bits, or you could see groupings of 8 bits separated with colons or dashes. It just depends on the vendor and how they decide to write the MAC address. All right. Ultimately, in the end, it's all binary anyway. Ultimately. All right. Which kind of brings us to this discussion that I wanted to have with you guys, which is how do we manage number systems? Because it's certainly something that we'll see later on when we get into subnetting. But let me digress here a little bit and kind of go into a different discussion here. In computing, I'm going to make the font a little bit smaller here because we're going to need quite a bit of space. So in computing, we can represent numbers in multiple ways. And there are 3 primary ways that we represent numbers in most of our modern computing systems today. Decimal, which is a base 10 system. Hexadecimal, which is a base 16 system. And then binary, which is a base 2 system. In fact, when you look at a Wireshark capture, you're going to see some numbers are represented as decimal numbers, Some numbers are represented as hex and some are represented in binary. So base 10 meaning 1, 10, 100, 1000, etc. Right? And base 16, we only have 16 possible values, 0 through 9, and then A through F, which is 16 possible numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then a base 2, obviously just 0 and 1. So any number can be represented in any of these formats. But ultimately, it's all about the binary, isn't it? I mean, ultimately, when we're modulating a signal, we're modulating a signal as ones and zeros. We're trying to identify ones and zeros. But again, different applications, different outputs, different types of data can be represented in different formats. For example, an IPv6 address is written in hexadecimal format, whereas an IPv4 address is written in dotted decimal format. All right? So I just want to do kind of a quick representation of how we can kind of move back and forth between these different number formats. I use something called the powers of 2 scale, or a radix scale, to represent essentially what we call the binary weights of each of our positions within this scale. So we have, let's say, for example, 2, 3, 4, 5, 6, 7, 8, 9, and I'll do one more, 10. 2 to the power of 0. I'm trying to do this as quickly as possible. 2 to the power of 1. 2 to the power of 2. 2 to the power of 3. 2 to the power of, oops. 2 to the power of 4, and so on. You guys get the idea, right? So this represents essentially my powers of 2 scale, which I then use to represent different numbers and different number formats. So 2 to the power of 7, 2 to the power of 8, 2 to the power of 9. I think that should be enough. And then I just have to kind of line everything up. Notepad is probably not the best choice here to do this with, but there's my 2 to the power 8, my 2 to the power 7, 2 to the power 6, 2 to the power 5, 5, 4, 3, 2, 1, and 0. All right? So if I do the actual calculation, this is 512, this is 256, this is 128, this is 64, this is 32, this is 16, this is 8, this is 4, this is 2, and finally this is 1. Those are the decimal weights of each of those binary positions. All right, and this is certainly something that you need to know if you're going to be doing subnetting and dealing with decimal to binary conversions and so on. And the bottom line is, if I want to represent any decimal number, I just have to have enough bits in the binary string that allows me to add up the columns to that decimal value. So let's say, for example, I am trying to represent, let's say 618 in binary. All right? That means that that column is turned on, this column is turned off, this column is turned off, this column is turned on, this column is turned on. So that gets me 96, 608, right? I think that's 608. What did I say I was going to try and do? 618? So I need 10 more. 1, 0, 1, 0. Okay? So 512 plus 96 is 608, plus 10 is 618. Okay? So that's 618 in decimal. And it's a really, really simple concept. If I need to go above 1024 or 1023, technically, I need to have another column. And so the number of bits that I have in my binary string really just depends on how large of a decimal number I'm trying to represent. And you can reverse this, by the way, by just doing it in the opposite direction. We did decimal to binary, but you could also do binary to decimal. And most of you guys are probably familiar with this. You've seen this before. You've done these calculations before. But what about hexadecimal, right? What if I want to represent 618 in hex? All right? We do a kind of a little bit of a different conversion here. I take my binary string, 10011101010, and from the right to the left, I break up this binary string into nibbles. Put some padding bits there. And a nibble is basically 4 bits. All right? So I break up the binary string into nibbles, and then I can convert each one of those nibbles to their hexadecimal equivalent. Now remember, hex is a base 16 scale. So hex would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And decimal would be 0, let me move this over, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Probably should have used Notepad++, but works out okay. All right? So this particular binary pattern is what in decimal? If you put it on the scale here, it's 2, right? So that is a 2 in decimal, which also happens to be a 2 in hex. This is a 6. Agreed? So that would be a 6 in decimal, which also happens to be a 6 in hex. And then finally, this one is what? It's a 10, which is an A in hex. So actually, 618 is equal to 0x, which represents hex. And we generally like to write our hex numbers in nice, even blocks. So we'll put a 0, 2, 6 alpha. Nice, even 16-bit block. So that's how you do your conversion from hex to decimal to binary and vice versa. There's not a direct conversion from hex to binary, or hex to decimal, I should say. You have to look at the binary string first, right? So for example, if I was to say 0x45AC, well, that's going to be equivalent to this in binary, 0100, 0101, 1010, and 10, 11, 12, 100. And then I would have to put this on my scale to see what the decimal equivalent of that value would be. Okay? A little bit beyond the scope of what they were talking about in this particular case, but and we'll see some more of this a little bit later on as we start to get into the subnetting discussion that we're going to have a little bit later on. All right? So MAC address is composed of 12 hexadecimal numbers. 12 times 4 is 48, 48 bits. There's 2 main components. The first 24 bits constitutes the OUI. So who assigns those OUIs? The IANA. That same organization we talked about yesterday that basically handles all numbers on the internet. The Internet Assigned Numbers Authority. Cisco has a few thousand of them, but basically any vendor that wants to manufacture products that require MAC addresses has to register for at least one OUI, but most likely multiple. Those get assigned. Again, it's really technically only 22 bits because we have those two special case bits that identify if it's a broadcast or multicast or if it's local or global. All right, and then the last 24 bits represents the vendor assigned portion of the MAC address, which is generally going to be based on like a serial number or something that's going to be completely unique to that particular device. All right? All right. So we've kind of already talked about what we're going to be seeing here in the next discussion, as well as in our discovery, is how does a switch function? But there are still a couple of things that we can still talk about in this particular topic. With regard to how a switch learns and how it stores the information, we mentioned this previously that we have content addressable memory, which just happens to be MAC spelled backwards, but content addressable memory, which is a memory location within the switch that stores the MAC address information that the switch learns from other clients that are, or from the clients that are communicating through that switch. This CAM table is locally significant to the switch. It's not shared from one switch to the next, and it's built locally and managed locally on the switch. But what is the purpose of this content addressable memory? When a frame arrives at the switch, there are two things that the switch is going to do with that frame. First, it has to identify whether or not the information about the source has been added to the MAC address table or the content addressable memory. So it looks at the source MAC address of the frame, it looks at what VLAN that particular port is assigned to, and it maps that MAC address to the port based on that respective VLAN. And we'll be talking about VLANs a little bit later on. All right? But then the switch has to decide, what am I going to do with this frame? Am I going to flood it? Am I going to forward it? We don't ever decide to drop it. Again, that's assuming we're talking about the idea that we don't have any additional security configurations on the switch that would cause the frame to be dropped, like an access list or some sort of filter. So the switch has two decisions it has to make. Do I forward the frame or do I flood the frame? Now in the book they also talk about filter, forward, or flood, but forwarding and filtering are basically the same thing, because if I'm forwarding the frame out of port 10, I'm filtering out of all the other ports that aren't port 10. Does that make sense? So filtering and forwarding are kind of the same thing. If the destination MAC address is not in the database, if the destination MAC address is not in the CAM table, that's when we make the decision to flood the frame, and we send the frame out of every interface except for the port that it came in on. If for some reason the frame itself, if the destination address is in the database, then what do we do with that frame? We forward that frame to the port that's assigned to that particular interface. Now, if we configure VLANs, that adds another kind of layer of complexity here, because a VLAN is really, it's something that's configured and managed at layer 2, but it creates separate layer 3 broadcast domains. So if a frame arrives on a port in VLAN 10, the only place that that frame can ever be flooded or forwarded is out of other ports in VLAN 10. There's no way that the switch can make a decision to forward that frame out of any port that's not in VLAN 10. That's where we have to have routing. We have to be able to route between VLANs, not switch between VLANs. All right? If the destination MAC address of the received frame is on the same port as the source, then we simply drop that frame. That's the only time we would ever drop the frame, because we basically received the frame on the same port that the frame is attached, or that the destination is attached to. So there's no reason to send the frame back. All right? So we maintain this table by looking at the source MAC address of the frames that are coming in, and then learning or analyzing that information, analyzing the frame header, looking at the source MAC, and then mapping that to a particular port. All right? So we have a couple of diagrams here. Step number 1, Pca generates a frame. That frame arrives at the switch. Thank you, sir. Now, the switch says, okay, let me look at my MAC address table. Port 1 already has the MAC address of Pca mapped to it, or it got mapped to it in the process of receiving the frame. The destination address in this particular case, it looks like it's supposed to be PCB in this case. So the destination address of the frame is PCB, but there are no entries in the table for PCB. So what does the switch do? It floods the frame out of every interface except for the port that it came in on. PCB and PCC receive that frame. PCC is supposed to simply ignore it because it's not destined for PCC. So PCB receives the frame, and now PCB wants to respond. As soon as PCB sends the response frame, that's when the MAC address is mapped to port 3 for PCB in the respective VLAN, and that's when we make our final decision, which is a forwarding and filtering decision, not a flooding decision, because PCA's MAC address was already in the database. It's a pretty simple concept, guys. I mean, this is not really difficult to understand, all right? But there are some little caveats, some little kind of pieces of information that the book doesn't describe, which is how long does that information stay in the database, and in what scenarios could I actually kind of override this behavior and force a particular MAC address to only be allowed on a particular port and so on. We'll talk about some of that as we get into our discovery here in a minute. All right? So the switch performs this learning. The learning is when the switch receives a frame, it examines the source MAC address. It performs one of the two following actions. Is the MAC address present in the table? If it's not, it adds the MAC address to the port number and the MAC address table and starts that timer that we talked about previously, that aging timer for that particular MAC address. That's not a fixed timer, by the way. You can adjust that timer value. And by the way, every time the switch sees a frame from that address, that timer gets reset. It's not just a 300-second timer that just simply goes down. As long as I'm receiving information from that source on that port, then we will go ahead and continue to re-up that timer. Is it possible for the same MAC address to exist on two different interfaces? It is not. Okay? So if for some reason MAC address A is on port 1, and you move that machine over to port 5, we'll just assume that the port status didn't go down. You move that machine over to port 5. As soon as that frame goes into port 5, the switch is going to rewrite its database and say, okay, this MAC address is now on port 5, and it's going to remove it from the previous port. All right? You can only have, the MAC address can only exist on one interface, the source MAC. Could I have more than one MAC address per interface? Could I have more than one MAC address per interface? Absolutely. If I have a downstream device that allows me to connect to multiple clients, like a hub or another switch, absolutely I can have more than one MAC address per interface. No doubt about it. All right? But again, this content addressable memory is not infinite in size. There's a finite amount of space to store this information. Now, granted, it could be hundreds of MAC addresses or thousands of MAC addresses and so on, but it is a limited amount of space. There's a function that you can actually configure on a switch called an Sdm Template. Let me see if I can pull up some information about that for you, because I don't believe the book gets into this. But this is kind of a unique concept to Cisco as well. Sdm templates. All right. An Sdm template is a way for us, this is a 3750 switch, but you can do this on other switches as well. It's a way for you to reallocate memory on the switch based on its primary function, right? So you have access, you have default, you have routing, you have VLANs, and basically what you do is you use the Sdm template command to allocate your ternary content addressable memory resources, a little bit beyond the scope of what we're talking about now, but basically it's just another type of CAM memory location to store either ACL information or VLAN information or MAC address information and so on. So the templates allow you to optimize the switch's memory allocation based on what its primary function is. Access, for example, maximize system resources for access control lists. So if you have a lot of security implemented on the switch. Default is kind of a balance to all functions. Routing means that you're going to allocate more memory to routing resources. That would be something that you would do like on a multi-layer switch. VLANs. The VLAN template disables routing and allows us to support the maximum number of MAC addresses. So this would be for a switch that's not doing any routing. You would set the Sdm template to VLAN so you could have the most number of MAC addresses. And you can see here the different templates and how many MAC addresses can I have if it's access, if it's default. So up to 12,000 MAC addresses if it's in VLAN mode, but only 4,000 MAC addresses if it's in access mode. Were you guys aware that you could change how the memory is allocated on a switch using these Sdm templates? Yeah. It does require a reboot because you're actually reconfiguring the ASICs for their function, but it gives you the ability to kind of change what the switch's function is. So just go out, if you want to learn more about this, go out to Google and search for Sdm templates and you can learn all about that. What if the MAC address is already in the database? Well, then I just simply reset the timer. Again, every time I receive a frame with that source MAC address, that means that that host is still there. So I'm going to go ahead and reset the timer and we'll start that 300-second aging timer again. All right. Unicast versus broadcast and multicast. Unicast means basically, is the destination MAC address in the database? If it is, I'm going to go ahead and forward the frame out of the port where the MAC address is mapped to. If it's not, I'm going to flood the frame out of every port except for the port that it came from. This is what we call unknown unicast processing. We try to avoid this as much as possible, but initially this is all that the switch does because it hasn't learned anything. It doesn't know anything, so it's going to continually flood everything. Broadcast or multicast forwarding, it depends. Certainly broadcast forwarding, that's always going to be flooded. And when I say flooded, I mean flooded out of every port that's part of the appropriate VLAN. If I get a broadcast frame that comes in on VLAN 10, I'm only going to flood that frame out of all the interfaces that are assigned to VLAN 10. I'm not going to flood it to every port in every VLAN. That's the whole point of implementing VLANs, or at least one of the major points of implementing VLANs is to isolate your broadcast domains. With multicast, traditionally multicast frames are treated like broadcast. They simply get flooded because the destination MAC address is not mapped to a port because it's unknown. First of all, it's a virtual MAC address. It doesn't belong to a physical host, so there's really no reason why that MAC address would ever get mapped to a port. But if you are running IGMP and you're running IGMP snooping on the switch can get a little bit more intelligent and it will start to forward or duplicate multicast frames rather than flood those multicast frames out of every interface. All right, which brings us to discovery number 2, excuse me. Let's see how this switch operates. So we're going to go ahead and load this up and get into the discovery. All right, so in this discovery, we're going to basically just make some observations about how a switch maintains its MAC address table, what it uses to control the forwarding of frames on the switch itself, and we're just going to investigate some basic functionality here. All the devices here are already configured with all of their IP address information, all their access information, and their the interfaces are functional and whatnot. So we're really just going to do some very basic observations here. It'll be a pretty quick discovery, just to reiterate some of the things that we discussed in the lesson. Task 1 in this case is for us to determine how the MAC addresses of the gig 00 interface for PC1, PC2, and router 1 show up. We're going to do a couple of grep commands on each of these to identify specifically what those addresses look like. So let's go ahead and go into PC1 to start with, and we're going to just do a quick show interface include address to see if we can see that information. So show interface pipe include address, oops, sorry about that, include address, and we can see that we have this MAC address on the interface. Actually, let's just do gig 00. That way we can filter out even more. Show interface F00, sorry about that. And we can see that the MAC address for this particular device is 7600. It has an IP address of 10.10.1.10. If I go back to PC2 now, in this case, and pop up the console, I'll do the same thing, show interface FA00 pipe include address, show interface, we need a T in there. We can see that this guy, PC2, has a MAC address of 7700 and an IP address of 10.10.1.20. Finally, we'll go into router 1, we'll do the same thing. And in this particular case, it's also going to be fast Ethernet 00. So show interface FA00 pipe include address. And this particular router has a MAC address of 7500 and an IP address of 10.10.1.1. All right. So the MAC addresses in this case are kind of similar to each other. Obviously, in a real world, the MAC addresses would be vastly unique, and we would be able to distinguish from them pretty easily. All right. So let's go to switch number 2 now, and let's take a look at what switch 2 has learned at this point. It should have learned at least a few things because, there's other protocols and whatnot running on this network here. So show MAC address dash table, and sure enough, we see the address information matches what we would expect to see. 7500 is PC1, or router 1, excuse me, sorry. That is connected to fast Ethernet or gigabit Ethernet 01, and PC2, which is seen on gig 02. All right, that's the 7700 MAC address. Both PC2 and router 1 are directly connected to switch 2, and so there are going to be frames that are being generated kind of on a regular basis in this case, because we're going to be seeing things like CDP and some other types of frames, maybe some spanning tree BPDUs and stuff like that. That's going to be generating traffic. The router won't be generating those BPDUs, but certainly the switches will, and the routers will be generating Cisco Discovery Protocol messages every 60 seconds. We don't see the MAC address of PC1 yet, but we do see the MAC addresses of other devices in the network, like the switches themselves. All right. So in the next step, we're going to clear the MAC address table, and then we're going to quickly show the MAC address table again, just to demonstrate that we are actually repopulating this MAC address table fairly quickly, right? We should see within a few seconds or so that the MAC address table gets repopulated pretty quickly. All right. If we do it very quickly, which we had seen originally, obviously, the MAC address table hadn't been populated yet, but it does get populated pretty quickly. The directly connected systems especially are going to be generating Ethernet frames to the switch. PC1 is basically one hop away, for lack of a better term, so it may not be generating data, or it may not show up in the table just yet. So if we go to switch 1 and we repeat this task on switch 1, let me pull it up real quick here, we should see a similar output. All right, so let's do a clear MAC address table dynamic, and let's do a show MAC address table, and it already populated pretty quickly. Let's do the clear one more time and show. There we go. So we're seeing the information from the other switch, and then finally we see some information from the PC. Again, there are frames, there is data that is being generated by these devices, even though they're not actually generating any raw traffic across the network. All right, now the next thing we're going to do is we're going to generate some traffic from PC1. We're going to ping its gateway of 10.10.1.1, and we're going to generate some traffic from PC2. So now this traffic is going to pass across both of the switches, and because the MAC address of PC1 is not yet known, and the MAC address of router 1 or PC2 are not yet known, maybe on switch 1, there will be some flooding of the frames, but the flooding in this particular type of network is going to be relatively benign. There aren't a whole lot of hosts, but in the end, all three endpoints, PC1, PC2, and router 1, they should appear in the MAC address table of both switches. So let's go to PC1 to start with. We're going to ping the router, and let's go to, let's also ping the other PC, which is 1.20. All right, and then I'm going to go back to switch 1, and I should see a fully populated MAC address table in this case. In fact, I do. I see the other switch, which is Delta Delta 00, that's switch 2. I see the PCs, and I see the router all on all in the table. So we have a fully populated table in this case. If I look at switch 2, I should see a similar output, not exactly the same, but I should see a similar output, and sure enough I do. There's the MAC address of switch 1 and the MAC addresses of the devices in our network. All right, so PC2 and router 1, they're actually both associated to gig 00, and gig 00 is that link that goes over to switch 2. All the frames that are destined for those MAC addresses get forwarded to switch 2 directly in this particular case. All right, in the MAC address table of switch 2, PC1 is associated with gig 00. And again, gig 00 is the link over to switch 1, and Ethernet frames are going to be filtered or forwarded directly to that particular client. Now this information will stay in the table. If I do a show MAC address aging time, we can see this. We talked about this in our lecture. The global aging time for this MAC address information is 300 seconds or 5 minutes. So as long as frames are being generated, as long as data is being generated, there's no reason why these MAC addresses should not remain in the table indefinitely. You know, if we haven't received any frames from these particular clients for a specific period of time, then in that particular case, we would go ahead and drop that information. All right? So that really concludes the discovery. It's a really basic discovery, but again, switches are relatively basic devices. They forward frames, they flood frames, or forward or filter, or flood frames based on what's contained in this database. Keep in mind, too, that these are dynamic entries, right? So these mean that these MAC addresses were dynamically learned. We could use something like port security to statically assign MAC addresses to ports. We'll talk about that in one of our future lessons. All of these devices are associated to VLAN 1, and these are the appropriate, specific MAC addresses for those particular devices. So we have one more brief section in our series here, and then we'll wrap up this section. So the last section we're going to talk about before we wrap up this whole session here, this whole section, section 5, is duplex communication. We describe duplex communication in either one of two ways, either full duplex or half duplex communication. Now, traditionally in the past, I mean, when we had hubs and bridges and older network devices, we operated in half duplex mode. Half duplex mode meant that we had unidirectional data flow, which means data can only go out or come in, inbound or outbound, but not at the same time. So I could send data or I could receive data, which basically, but I couldn't do it at the same time, which basically means that in that sense, we're basically dividing the amount of bandwidth that we have in half. In addition, this would make it extremely difficult to avoid collisions. Half duplex communication often would result in collisions because the sender and the receiver might actually try to communicate at the exact same time. A switch will be sending a frame to a client, and the client will be sending a frame to the switch. They didn't have, within that time slot, they didn't have the opportunity to identify that there was a potential communication occurring because they didn't detect it, and they happened to both communicate at exactly the same time and cause a collision. It's just not a very efficient way to communicate. So what they came up with is this full duplex communication. Full duplex communication means that we had simultaneous conversations, right? I could send information and I could receive information. Both endpoints or both devices could communicate at the same time without the risk of the information colliding, because we had a separate physical transmit path and a separate physical receive path. That bidirectional communication means that we had less wait time to send transmissions. We effectively, in that sense, had more bandwidth because we could communicate more often and more frequently, and it's just a much more efficient way of communicating. And because really there's no possibility for us to have a collision, the collision detection feature, which is normally turned on in half duplex communication, gets turned off in full duplex communication. This only works on point-to-point connections, basically connections between switches, if you will. They have to be dedicated switch ports, and it does require that both sides operate in full duplex mode. That's a very important concept. All right. The duplex command does allow us the opportunity to modify that configuration. Let's say, for example, let's do a show IP interface brief. We'll use gig 3.3 in this particular case. Show run interface gig 3.3. And one thing I'm going to have to do is turn off the auto negotiation on the interface explicitly. So interface gig 3.3, no negotiation auto. And now I can set the speed to whatever speed I want to set it to. In this particular case, 10 meg, 100 meg, 1,000 meg, or 1 gig, or auto. Interestingly enough, if I do auto, and for some reason negotiation fails on this particular device, it's going to basically revert to the least, what it assumes would be the least common denominator, which would be the slowest speed and half duplex. So let's set the speed to 100, and then we have three options for duplex: auto, full, or half. We can set the duplex to half. Obviously, you wouldn't do this in a production environment, but now if I do show interface gig 3.3, I can see that this interface is operating in half duplex mode, 100 megabits per second, and those are the values that I actually configured. There may be instances in certain scenarios where you're connecting to third-party hardware, or maybe hardware that isn't as efficient, and auto negotiation tends to fail. In those particular scenarios, we want to make sure that we hard code the speed in duplex, because we don't want to end up reverting back to some sort of slow bandwidth and half duplex communication. All right, so we'll wrap up this lesson. We'll see you guys in section 6 in a little bit.